The study of what are the fastest algorithms and what are the ultimate limits to the algorithms. The story is basically will be split in 4 parts, and I apologize if it will probably be quite superficial, so I want to get an overview of these ideas. Please feel free to interrupt me. So basically what I will start with is I will introduce Kronecker coefficients and some natural problems related, I guess more general branching coefficients and multiplicities in representation theory that people have been interested in studying. Then I want to discuss 2 very, unorthodox motivations to them. So, internally inside mathematics, of course, it's interesting to study multiplicities and branching rules, but also outside of mathematics, say in theoretical quantum physics and theoretical computer science, there's some surprising sources of these problems I want to talk about. Then, we get to this point. Then I want to give you a primer, 5-minute overview of computational complexity theories, what are the basic ideas, what are the questions that people try to tackle. And then I hope to come back and talk a bit about some little results on actually the complexities of the computational complexity, the computational difficulty of representation theoretic problems. So this maybe hopefully closes the circle. So this main protagonist in this talk will be Young diagrams. So I'm sure all. So who has seen a Young diagram in the audience? Don't be shy. Excellent. Okay. So for me, Young diagram, it's a fancy name for a simple concept. So you can say it's just a partition of some number k into n parts. Okay, most n parts in my case. You could also think of this as an arrangement of boxes. There's at least there's not less boxes in the row. The number of boxes monotonically decreases as you go down. For example, here there would be 2 boxes in the first row, 1 in the second, 1 in the third row. You can think of this as a partition 2, 1, 1. And I will denote the lengths of these rows by lambda 1 and lambda 2 and so on. So these are unordered partitions, I guess. The reason why they're interesting in this talk is that they parameterize 2 interesting things. They parameterize the irreducible representation of the symmetric group, namely the symmetric group of k elements. Its irreducible representations are called specht modules, and they are labeled by Young diagrams with k boxes. So this is the k. On the other hand, all polynomial representations of the general linear group, say, are also labeled by Young diagrams, but now if the general linear group is G and M, then we look at Young diagrams with at most M rows, but the number of boxes is 3. So this is somehow k in the row of k in M. These are called Y modules, lambdas of the highest weight. Now, whenever we have representations, we can build new representations out of old ones, and we can decompose them again in their individual building blocks. And so, very classical but rich sorts of problems. So here are 2 simple and well-known decompositions. So the first, I guess, is so the physicists call this the Clebsch-Gordan rule. It's basically a special case of SU2. So for SU2, you have Young diagrams with 2 rows. You can equivalently record. If you care about SU2 raw value, you can just look at the difference of these row lengths. If you divide them by 2, this is what physicists like to call the spin. So this is a Young diagram corresponding to spin I representation. You can take 2 of those, EI and EJ, and then it's somehow known that this is a multiplicity-free branching decomposition, branching series, where some of the spin goes between I minus J up to the value. This is a very classical decomposition. It's interesting that somehow all the coefficients in this sequence are 0 or 1, so the representation occurs not at all or exactly once. A more interesting one, and it's also very useful, is Cauchy-Y duality. So for Cauchy-Y duality, we look at the representation Cm with the tensor k. So on this representation, we have both an action of the symmetric group by commuting tensor factors, so the symmetric group Sk, and also the general linear group GLM by its diagonal action. So we can join, and these 2 actions commute, so we can jointly decompose this into irreducibles. And the claim is that actually these irreducibles, well, the irreducible representation of this product group, they are just tensor products of an irreducible GLM representation and an irreducible SK representation. And the claim is they actually line up nicely. So with any Young diagram lambda, it's the same Young diagram, here and here. And the direct sum is basically over all allowed ones. So it's over all Young diagrams that have k boxes and at most n rows. So this is a nice duality sort of that sort of brings together combinatorics, if you like, and D theory. Okay, so one particular representation is when the Young diagram is just like a single row and k boxes. For example, this would be the symmetric subspace corresponding to the trivial SK representation and the symmetric representation of GNM. More generally, one can look at the following objects. So here I decomposed two tensor products, a tensor product of two SU2 representations. I could also accept U2 representations. Now we look at general GLM or UM representations, and now come the so let's take two Young diagrams lambda and mu. Let's decompose the corresponding GLM representations into irreducibles. There will exist some coefficients, C lambda mu. There's a new label nu, and then this number now denotes the multiplicity of the irreducible representation labeled by Young diagram mu in this sense. So these coefficients are called Littlewood-Richardson coefficients. They're sort of very famous and they have been studied for a long time, and we know actually a lot about them. So, for example, there's the famous Littlewood-Richardson rule, which says that actually the multiplicity has a nice combinatorial description. It's just counting certain things called Littlewood-Richardson tableaus. Okay. So basically, what you do is you take one of the Young diagrams, you somehow remove another one, and then you fill them in according to certain rules. And the rules are not important for the talk, but the important thing is that it's very simple combinatorial rules that you have to satisfy. So it's it might take a long time, but it's at least easy to count them. You just you can try all the options, and whenever you find one, you know that this coefficient is one more than you knew before. More recently, there have been other descriptions of this coefficient. So, for example, there's the so-called honeycomb or
okay. It's just that I never understood what was going forward becomes right.
Yes, not in this talk. Okay. Not in this talk. Yes, I think. Right.
Okay.
Yes, let's maybe not zoom in, but let's just say that there's two more modern descriptions, which are all equivalent. One counts certain things called integral heights, which are somehow filling up of such a grid of numbers, where you have certain boundary conditions, you have a certain filling rule, and then you just try to fill this up with some numbers, and you count the number of possible fillings, something like this is then called integral height. And there's another thing called honeycombs, which is somehow diagrams which somehow have asymptotic lines going out to infinity. So there are just three different representations. So Knudsen and Tau, I think in their paper eventually they only discuss this one. And I think Huber explains how these are related. But maybe don't zoom into why they are the same. But the point is just that somehow we have a good handle of these coefficients, in part because they count very nice and clean combinatorial gadgets. Okay. But in particular, these formulas that are all these three formulas, they are obviously positive formulas, right? Because they count stuff. It's clear, like as soon as you found one, you know the coefficient is not zero, which is nice. And in fact, this can be lifted, so you can actually tell a computer to very efficiently check if a Littlewood-Richardson coefficient is zero. It's actually not that. It's an easy problem, and it's something to make precise. So here's another. Yes, to just check it is not zero is not difficult, and I will talk about what this actually means, what not difficult means more formally in the second part. Maybe just some other properties that we know that are very useful. One is the so-called saturation property. It basically says whenever we have three Young diagrams, lambda, mu, we can always rescale each row of this diagram by some fixed number. It will give us a larger diagram. So I guess I don't have a diagram here. Let's just say we have this one 2 times this diagram. We have 4 boxes, 2 boxes, 2 boxes. And so what the saturation property says is that if after some rescaling the coefficient is positive, then actually it's already positive without the rescaling. So somehow all this asymptotics is not hard, right? Somehow if you only care about 0 and non-zero, and not about the actual number, it's somehow you don't have to rescale. And it's somehow closely related for reasons that are not obvious at this point to a question in symplectic geometry, actually a question in linear algebra, but which has a symplectic geometry interpretation. It's related to a famous problem. It's basically related to the following problem: given three-dimensional matrices A, B, C, such that A plus B equals C, what are the relation on their eigenvalues? It turns out that actually this eigenvalue equation is precisely equivalent to knowing if a corresponding little Richardson coefficient is 0 or non-zero. And somehow the reason that because this is saturated, we actually don't have to check infinitely many little Richardson coefficients, but only one. So somehow all these things are connected, and then there's these famous Horn's inequalities that just give you like a complete complete list of the characterizations of these eigenvalues, etc., etc. And I will sort of clarify this in a different context in a second. So here are some other coefficients that are, look very similar, but are somehow much less is known about these. Well, a lot is known, but somehow they seem just more difficult. And they're defined just in the same way as before, except that now we decompose tensor products of symmetric group representations. So I have take three Young diagrams, lambda, mu, mu, say all with k boxes. Well, two Young diagrams, lambda, mu, with k boxes both. I take the tensor product as sk representation, I decompose them into reducibles. I get again multiplicities, they're called the Kronecker coefficients. And I want to explain in a bit that actually these are interesting coefficients on their own, but they also have actually they rise in sort of very unexpected applications, if you like. There's an equivalent way of defining coefficients, not using the symmetric group, but using the general linear group. And here's one way of doing it. Take Cm, tensor Cm, tensor Cm as a representation of GLM irreducible, but now we take the k symmetric power. So then it will not be irreducible in general. And so we can decompose it into its irreducibles. All irreducibles of this product group, they are tensor products, V lambda, tensor mu, tensor mu, and the corresponding multiplicities are the same as defined above. One can see this using the Schur Y duality that I discussed on the second slide, but otherwise it doesn't use it. So somehow there's a combinatorics way of seeing it, there's a D group way of understanding these coefficients, and both are somehow very useful. I should also say that the Littlewood-Richardson coefficients are special Kronecker coefficients, so they are subclass. For special lambda mu nu, one actually recovers the coefficients from before. So what do we know about Kronecker coefficients? We know quite some things, but sort of explicit knowledge is it's very difficult. So in very special cases, we have explicit formulas. So I think for two rows, if two of the Young diagrams are two rows only, and the next one has 4 rows at most. In this case, I think there's explicit formulas, so-called quasi-polynomial formulas. Yeah, then we also know explicit formulas for so-called hooks, which just look like hooks, if the diagrams are hooks. More recently, people have studied, other special Kronecker coefficients. For example, Kronecker coefficients where you have the staircase partition. So there's some conjecture that somehow in the tensor square of this one, all the representations occur. I think it's like a conjecture. No, people have worked on this, but it's still open. I think all, or maybe there's some like trivial constraint that I forgot, but it's essentially yes, that's okay. Right. But the big question is so what we do not know is we don't have a combinatorial interpretation of these coefficients. So we don't know what they count, except that they count irreducible representations in some, in some decomposition. But there's no gadgets that, it's not like some tableaus that you have to count with some heights or something like this. So this makes things very difficult. So we can, of course, write down abstract formulas, using, say, from character theory, but they will always have plus and minus signs. So it's very difficult, for example, to check if this number is positive or it's 0, because there's all those cancellations. So that's part of the difficulty. One thing that we do understand is a certain kind of asymptotics, and it's a asymptotics I mentioned before in the context of the Littlewood-Richardson coefficients. So the one where we rescale all these rows by some number. And one way to make this precise is the following. Let's just look at if you like, at the support of the Kronecker coefficient, defined in the following way. Let's look at all triples of Young diagrams, lambda, mu, mu, that have at most m rows, and for which the Kronecker coefficient is positive. So this is just some set of points. We can think of it as a subset of z to the 3m, if you like, right? There's m coordinates, integer coordinates for lambda, m for mu, m for nu. And we will get some collection of points like these green points over here. the claim is that, in a sense, this object is well described by a convex cone. And what I mean by this is the following. There exists a convex cone with the following property. If you are outside, so this is the cone in this picture. If you're outside the cone, then the Kronecker coefficient is always 0. Like it's never 1. If you're inside the cone and you go along a ray, so for example along this gray ray, then at some point it will become non-zero. So even though g lambda mu nu might be 0, there exists some scale, stretching factor s, that the g s lambda, s mu s nu mu nu, and then divide them by k by the number of boxes. Then this is like invariant under rescaling. Like if I take s lambda, s mu, the number of boxes will also scale by s, so it's the same point. So this object up to closure, or it's a convex polytope over the rationals, it turns out. So, because we compress all the lines to a single point. So one can study this more generally. So this is an instance of a moment polytope in the language of symplectic geometry. And in a sense we know explicit inequalities. So Alexander Kirchko has written some down based on work by Bernstein and Germain. Nicolas Vessier has sort of discovered a type characterization, sort of like a irredundant set of inequalities that bound this polytope. And with Michel we have tried to sort of distill this into a sort of a very concrete form so that we can actually compute these things on the computer. It's also, so one reason why this polytope is interesting is because of this moment polytope connection, there's actually a linear algebra way of characterizing the cone. So remember that before I told you about how these little Richardson coefficients were somehow related to the eigenvalues of sums of matrices that say add up to each other. Now there's a similar phenomenon here. So these Kronecker coefficients, G lambda mu nu, they're related to something that's a bit more complicated to describe. They're related to the moment polytope of some easy projective space, but with a complicated, well, actually not a complicated group action, but it turns out that the thing is complicated. So basically the idea is you take a point in projective space, say, CN3. Now, on this space, there's a GLM3 action. You have an induced action of the Lie algebra, you have a dual action of this. And then so you can obtain from this point, you can obtain 3 matrices. Maybe I will not just explain this, because it's also important for the talk. You can kind of from one point in this projective space, you can obtain 3 Hermitian matrices, which are all m by m matrices. You can look at their eigenvalues, and again, these eigenvalues will be a geometric description of this polytope. Okay, so this is basically just, you have this action on the vector space, it's an action on the projective space, you have sort of a dual action, and so on and so forth, and then this gives you maybe, again, you can ask me maybe about it later. The point is that this map actually has an interpretation of quantum physics. It's somehow related to, you have some system of 3 quantum particles, A, B, and C. They are in some common state, psi, and you are interested in the states of the individual particles. So this is called the quantum marginal problem, because it's like a probability distribution, and you sum or we integrate out 2 of the 3 random variables. So somehow the relation between a joint probability distribution and its marginal distribution. So this is the quantum version of it. It's called the quantum marginal problem, and it's precisely describing this Kronecker polytope. Okay. And whatever the exact definitions there's somehow an external motivation why I'm very interested in computing these polytopes. And I mean, in particular, interested in doing this efficiently, like actually producing the list of inequalities. In the same way, okay, as I explained, the Richardson coefficient they give rise to again some polytope of eigenvalues found by Holmes and there's a second motivation which maybe I will dare go into, and then I see maybe I will not dare go into. Right. Let me maybe briefly talk about this because it's kind of cute and it's a nice application. So it's a nice application. So somehow completely independent setup. Let's ignore everything I've said so far. Let's look at the following problem. Let's take 2 matrices, 2 2x2 matrices, A and B. Let's ask, okay, how do we multiply matrices? If I do it in a row by times columns, so for example A11, B1 plus A1 B1, that's right. Something happened here. B1. So to compute this element of the result, I use two multiplications. Okay, two sort of elementary multiplications, these red dots. Now I have 4 such outputs, so in total I have 4 times 2 equals 8 multiplications that I use. Okay. You could ask, is this optimal? Can I do it with less? It turns out that actually 7 multiplications are enough. And it's kind of a crazy long expression, and you of course do many more additions than you would do otherwise, but in the end you can do it with 7 multiplications. And so this seems like a funny artifact, but actually you can do this recursively. It works non-commutatively. You can do it recursively with block matrices. And so you get essentially an algorithm for multiplying n by n matrices that runs, that uses only n to the second logarithm of 2 of 7 in this case, n to the 2.8 multiplications to multiply the matrices. Right? And the naive operation would be you have n squared many entries in the result, and for each one you need to do n, right? Like I did here. So somehow this is very surprising. Okay, this is much better and actually useful. Now people have tried to push this further. They ask, what is the best algorithm that you can do? The best.
You don't care about the number of additions.
At this point, I don't care about the number of additions, and you might ask, is this really realistic? It used to be a realistic assumption. It's not so realistic anymore, I would say. Yes, then that's that. Now sort of the problem has
Just care about
solved.
the number of multiplications that you.
So in a sense, counting only the multiplications is relevant if you think about very large numbers. Then clearly multiplying will be more complicated than adding, because the moment you add and gain one more digit. Yeah. But if you multiply, things become so. Somehow multiplying is somehow requires something between quadratic, almost quadratic. Also, you can multiply faster than quadratic, but say multiplying two numbers almost requires quadratic effort, and adding it only linear. So it makes sense. So the
Could you say how you reduce to this from 8 to 7?
not on this blackboard, to be honest. So it's a bit of a tricky reduction actually. So I am hesitant. There's a simpler version where you multiply polynomials and you can do a similar trick. So this one maybe I can. So okay, maybe to give you I realize I will probably not make any time limit. So let me try. So suppose you multiply two polynomials like this, c plus xc. So the naive thing would be ac, bc plus acx, and then x squared. So this would be 1, 2, 3, 4 multiplications. But now you could also do something. Suppose you only compute a times c, you compute b times e, and you compute a plus b times plus d, and right, this is a, c, a, b, b, c, d, e. Now, you do only 3 multiplications, but now you take this one and you subtract ac and you subtract bd, so you actually get this guy. So, this one you have, this one you have, and this one, and this one, and this guy. So now we did it in 3 instead of 1. It's somehow more complicated, but a similar spirit. So adding is fine, even multiplying by fixed constants is fine. But yeah, that's right. And the big question now here is, okay, one question of course, how good can you do it? The best algorithms due to others, Virginia Mathematica Williams and not even around actually, is something like n to the 2.37. Okay, so it's actually very close to quadratic already. The big question is, can you multiply two n by n matrices in almost quadratic time, which sounds crazy, but there's no reason not to. So how would you attack showing that you cannot do it? So how would you prove lower bounds? And so there's a sort of a very unorthodox approach to it that's sort of pioneered by Peter Maloney and Sohony, in this instance by Vergata, which is basically, okay, let's study using algebraic geometry. So why should algebraic geometry help? Well, we can take matrix multiplication, which is a bilinear map from matrices, tensor matrices to matrices. We can think of it as a tensor in some threefold tensor product, n by n matrices and the dual space. Okay. Likewise, we can look at the following tensor, which are called the easy tensor. It's just like ei times ei times ei, where it's like some standard basis, and you go up to some r. Okay. This is somehow the universal tensor for doing a single multiplication of the kind I did here. Now there's this natural sort of symmetry group, which is GLN times GLN times GLN, which sort of transforms this one into an arbitrary, sort of arbitrary products, an arbitrary product like this.
What is the R?
R is something I choose. Let's say I choose R. So for any R I could write this down. And for any N I can write this down, and I can embed both in some bigger CM tensor
R
series.
for the moment you choose R and you act by GLN.
That's right, so I act by GLN, GLN. And what I want to show is that the hard tensor is not in the orbit or even in the closure of the orbit of the easy tensor. If I can show this is basically equivalent to saying I need more than R elementary multiplications to multiply two N by N matrices. Okay. And so the idea was, let's actually study these varieties. Maybe let's find equations and let's show that the hard tensor does not satisfy the equations. So Joe Lensburg used this to actually show that 7 is optimal for the 2 by 2 case. So he actually wrote down equations for tensor ranked, so-called tensor rank 6 tensors, and he showed that the matrix multiplication tensor violates such an equation. But now to study this asymptotic question, somehow you have to do this for all n, right? So for like a sequence of n that goes to infinity. And so, we have to relax and we have to make the problem simpler. So instead of, let's say, instead of actually studying these orbit closures, let's maybe study their ring of functions, and let's only look at the representations of inside this ring of functions. So one way to prove this non-containment would be, let's take the orbit closure of the easy tensor, let's take the one of the hard tensor, let's find the representation in there which is not contained here. But clearly, the point cannot be contained in the orbit closure. And now it turns out if one decomposes these coordinate vectors degree by degree into irreducibles, one obtains coefficients which are not too dissimilar from Kronecker coefficients. So there's some certain Kronecker coefficients, there's something called symmetric Kronecker coefficients, plathisms. So it's all kind of these, very classical representation theoretic objects. And so this is, say, another reason, so which is somehow dear to my interest as well, why one should study Kronecker coefficients. And actually the ones that appear are very special. For example, something that one needs is two rectangular partitions and an arbitrary third one. And the question is basically, is such a thing zero or is it non-zero? So, and I should say that actually I think much of the recent work in Kronecker coefficients, also in pure mathematics, has been motivated by this connection. So I think Kumar and Vasea and so on, they have actually studied sort of, maybe more algebraic geometry questions, but some of the things that are very much in the spirit. For this motivation, I think.
But you said they have found some lambda satisfying that. They found some.
Yes. So I think there's sort of proof of concept that this works. By Burgess and Ekenmeyer, they actually found some representation like this, but they get a very modest bound. They get something like, it's not they get a lower bound of n squared plus something linear, I think. So not a better exponent, not an exponent that is larger than 2, not n to the 2.1. It's like a big open question to get something like this. And some people think it's actually not possible. But they have like a linear term, something like, I forget, n squared plus some constant times n, maybe something like this. And this they get from this method. So they actually identify sequences of representations. Okay. All right, so maybe, so now of course I'm completely lost in time. Let me just maybe recall these non-applications or the mathematical challenges that I mentioned before. So again, these are the Kronecker coefficients. So the three interesting questions that I want to focus on is the first is, how do we decide, well, I want to understand when is the Kronecker coefficient zero non-zero. I don't want to compute the number, just understanding when it's zero non-zero. Okay. And again, these asymptotics, somehow we understand more or less, but some of the failure saturation makes this problem different and more complicated. Second task, which is sort of out of reach at this point, I would say, is find a positive combinatorial formula for the coefficient itself. The third one is maybe a less sharp question. It's sort of saying, let's try to understand these holes in the cone. Do we have like a systematic way of producing holes? How to understand them? Where do they occur in the cone and so on? I guess this may be more just to understand the structure. There's no such clear. Okay. And so somehow what I want to propose and what I wanted to discuss in this talk was to actually, all of these problems are somehow difficult. and the idea is kind of, let's study this difficulty very formally. Let's actually study how difficult is it for a computer to answer these questions? And maybe we learn something from mathematics. Okay, so now comes a couple of slides where I just want to introduce the language. What is the precise language how one phrases this question? And so it's a little tutorial into computation complexity. So what is computation complexity? From sort of a high level, it's basically a study of it's the study of the difficulty of a computation problem. So what is a computation problem? So we have like two basic classes. One class is the so-called decision problem. It's a question that has a yes and a no answer. Okay, so there's some input, we call the problem instance. It's encoded in some concrete way. For example, it could be a number in binary. And then we want to find some algorithm, say. So in some form and model, for example, a Turing machine, a computer program, a Fortran program, I don't know. And then in the end, we should get an answer. Again, the answer is some specified format. Maybe it's just a bit that tells yes or no. This would be an algorithm for a decision problem. For example, the one is n a prime, and the answer would be yes or no. We can also have a counting problem. For example, we can ask how many prime factors does n have. The problem instances n. The answer will be this number of prime factors, say in binary, and we want to find some algorithm. And the central question in complexity theory is really how fast of an algorithm can we find. And so to measure it, the answer that we're interested in is not something like, okay, it takes you at least 1,000 operations, because the number of operations will really depend on which computer you use, what operations does it have. But we care about the asymptotics. So for example, if we have a number that takes, has n digits for some large n, how many operations do we need to decide if it's prime? Okay. How does the number of operations scale with n? Is it a polynomial scaling or is it an exponential scaling, for example? So complexity theory is not about finding algorithms, but it's finding these ultimate bounds for fast scaling. And there's some sort of broad categories that you can put problems into. There's one class of problems that is called a P, and it's those problems that have an efficient algorithm. And now efficient means it runs in polynomially many steps, but the polynomial is in the input size. Okay, so again we have a number with n digits. Then the claim is there should exist some polynomial so that the algorithm runs in p of n steps. And these are some of the easy problems in a way, so at least the theoretically easy problems. So many linear algebra problems, matrix multiplication, it's at least n cubed, so it's an easy problem. It's a problem in P, Minkart, Max's law, and often we use some duality, some like sharp algebraic structure to solve these problems. And then one can zoom in and ask what is really the fastest one, like it's n squared, it's n cubed, it's n 2.5, etc. But on this perspective, we just care about polynomial time. On the other hand, there's a class of problems called NP, which is much more general. It's basically the problems where we don't know how to find the answer, but I can easily convince you if the answer is yes. So for example, you could say it's actually hard to factorize a number into individual pieces. But if I give you a factorization, you can just check it. You just check each one is prime, and then you multiply, you get the result, and you're happy. So there's a certificate, and you can check efficiently the answer. For example, you could ask, can you color a graph using 3 colors? This is some of our famous problem in NP. And we don't know how to find such a coloring. But if I give you a coloring, you just easily check, it uses 3 colors, and neighbors do not have the same color. So it's easy to check again. So these problems we call NP. It's the one where the answer is yes. I can easily convince you using a small, that is polynomial size certificate, which can again in polynomial time be verified. If the answer is no, then there should be no way I can convince you. For any such certificate, you will say no, that's not a good coloring. Okay, the central conjecture of this field is P equals NP or not. So we don't think it's the same, right? Some of for philosophical reasons as well as that people tried for a long time. It's kind of like saying, as mathematicians, it's kind of like, I give you a proof, then as a referee, it's maybe not so hard to check. Well, I guess sometimes it actually is hard to check if the proof is correct. But surely it must be harder to find it. So this is the same philosophy that people think, why this should be a correct statement. Okay. Just like I defined NP, I can also define co-NP. So co-NP is just like NP, but now it's the other way around. It says, if the answer is no, I should be able to convince you easily. Okay, but otherwise, okay, there exists no such certificate. So it's interestingly asymmetric. So for polynomial time, I can just compute the answer either it's yes or no. But in this case, that's actually different. And so this is somehow the conjectured landscape of complexity theory, like a small part of it. It's like, here are the problems in NP, the one that we can easily check the answer is yes. Here we can check easily that the answer is no. These ones in P, they are both in NP and co-NP. They are the ones that you can do efficiently. And then there's also problems that are both in NP and in co-NP, but where we don't know efficient algorithms. These are problems like the graph isomorphism problem, where recently Babai has actually proved an algorithm that is almost polynomial time. So these problems, even though they include problems like factoring, we think of them, they are not the generically hard problems. They are somehow, yeah, in a sense that I will make precise in a second. Whereas like the problems out here, there's some that are really hard, so where we don't believe there will be something efficient ever. So some of the problems, okay, the speed coloring problems maybe will go. Or integer programming, you have like some linear equations, but you want to solve them over the integers, not over the real numbers or the complex numbers. So this is also a well-known hard problem, because all of combinatorics can be reduced to it. Okay, so how do we compare complexity? So the way of comparing complexity, because you cannot prove anything, right? We don't even know if P is equal to NP or not. So how can we prove something? So the way we prove things is by reduction. So we show that certain problems are at least as hard as others, or at most as hard as others. So for example, we say that X can be reduced to Y if we can solve X if we had a nice algorithm for Y. Okay. So basically we can use Y, the algorithm for Y as a black box, even if we don't know it exists. We just take an algorithm for Y, and then we build a solution for X out of it. We say that, and then, so using this notion of reduction, we say that a problem is NP hard, for example, if any problem that is an NP, as I defined it before, can actually be reduced to it, right? It's like a universal problem of this kind. We say it's NP complete if it's both at least as hard as all the other ones in NP, but it's also itself contained in NP. So those actually are the really big universal problems in NP. And there's this amazing theorem that such things exist. So for example, if you know how to decide if a graph has a 3 coloring, you can solve all the problems in NP. There's always reduction, there's an explicit reduction to it. And many combinatorial problems are of this kind, and there's a little tree that you cannot read, but it's like a sort of a family tree of computation problems, and the arrows mean reduction. Okay. Conversely, if for any NP complete problem you find a fast algorithm, you have proof that P is equal to NP. Because it's sort of any other NP problem you can solve using the complete one, and then you show for the complete one that's in P, then everything would collapse, the entire picture and move the problem. The last point I want to discuss complexity of counting problems. So NP and co-NP, they refer to yes-no problems, is the number prime? Okay. What is a good class of counting problems? Okay, we could, so clearly polynomial time still makes sense. So we could hope for an algorithm that runs polynomial many steps, and at the end it just prints out a number. So this is still a good notion. But NP does not make sense because the answer will now be number. So one thing that is actually very natural is to define a class that's called sharp P. It's just the number of certificates that is accepted by an NP algorithm. Okay. So for example, the 3 coloring problem is an NP problem. Counting the number of 3 colorings for a given graph would be a problem in this class sharp P. Okay. So it's a natural class for counting things where each instance you can easily verify. Okay, for example, heights, counting these integral heights. You can just whenever I give you one, you can check if it satisfies type conditions, and then you say, okay, I increase by 1. Somehow counting the number of certificates for an NP problem is a very natural class, and it has sort of an operational meaning. It really means it's maybe hard to compute the number in the end because we have to go through all the options, but there's a clear strategy. And obviously it's positive in the end what we get, right? Because we count certificates. It's again a counting interpretation. And so Keita and Harmony basically proposed that this is actually a sharp and a precise definition of what we could mean by a positive combinatorial counting formula. That was proposed. Right. And very good. Can I check the time once again? So it's probably minus 10 minutes. Yes. Okay, still have 15 minutes. No?
Yeah.
Okay, so now we introduce all this funny language with P, NP, CoNP, sharp P, and so on. Now we want to apply this language to representations. I mean, now we have the language and we can try to prove some results. What's the problems that we're interested in? Well, naturally, suppose we have some branching problems. So we have some representation, we can go compose it into irreducibles. And clearly there's a decision and a counting problem. The decision problem is decide if a certain irreducible representation B lambda occurs in V. Answer yes, no. Counting problem is actually compute the multiplicity. So we can actually use this language and do this before. Now that's a sort of a small fine print, namely that if I write down one representation, you can just do the answer, remember it in your head, and there's nothing interesting to prove, right? Because well, either it occurs or it doesn't occur. Everything is finite. So we should really look at some family of representations. For example, we can for example, the ones in the little Richardson and the Kronecker coefficients. There we had some family, right? We had, for example, different lambda times of mu's. So now if you vary the Young diagrams, you vary the representation. So it's like a whole family of representations, and I will explain to you, what is the input and so on and so forth. So this is what we should do. Here's the Richardson coefficient. Again, two GMM representations, where M is now free. M is not fixed anymore. Okay? So the input to this computation problems now is the following. It's three Young diagrams, lambda, mu, and nu, such that somehow lambda plus mu should equal to nu. So the number of boxes in lambda plus the number of boxes in mu should equal to the number of boxes in mu. This is the input. Okay, decision problem asks, is the little Richardson coefficient 0 or non-zero? The counting problem asks, compute the little Richardson coefficient. And so now we can sort of phrase what we said loosely before as a theorem. So the theorem of Malmedy and Sahoni says that actually to decide if this coefficient is 0 or non-zero, we can do in polynomial type. So we can actually do it efficiently. Actually also in practice, like one can write programs for this, and it's very useful to do experiments. And the proving relies on the honeycomb or hive machinery and some ideas about linear programming and something about integral points. Okay. Anyway, so this basically using these like highly non-trivial mathematical structural results, we can solve this problem. On the other hand, to actually compute the coefficient in its full glory, so that to actually count how many times a representation occurs in the tensor product, it's a so-called sharp P comp P problem. So it is in sharp P, and it's as hard as any other problem in sharp P. Okay. And so what does this mean? So it means crazy things. For example, it means that they exist and that you can actually write down a mapping which takes, say, graphs, and for each graph it produces a triple of Young diagrams, lambda, mu, and then the graph has a 3 coloring if and only if the little Richardson coefficient is non-zero. Okay, so that's right. The other thing, yes, you're right. So this number is right. That's right. And so somehow, yes. So somehow this is kind of. Okay, maybe I should also say how one does this. So to show that this is true. Yes. So to show that this is true, I guess what one does is, well, just the combinatorial formula for the little Richardson coefficient in terms of counting at R tableaus shows that it's in sharp P, and somehow to show that it's hard as one identifies some special partitions for which somehow the little Richardson coefficient is counting well-known hard things, something called contingency tables, which someone else already showed that they are. So that's kind of the landscape. Now we can ask for the Kronecker coefficient. What's the situation there? And there actually, so similar problem. Now we're given 2 Young diagrams with the same number of boxes, and we can ask, is the Kronecker coefficient 0 or 0, and how hard is it to count to determine the number? And here actually, well, the counting problem is already at least as hard as the little Richardson problem, because that one was hard, and Kronecker coefficients are more general than little Richardson. So this is easy somehow. But we actually don't know if it's in sharp P, and this is really a sharp version of the question, is there a combinatorial formula? Okay, so this is just rephrasing some of the whole problem. On the other hand, for the decision problem, it was also believed, somehow conjectured, that it could be NP, and there we could recently show that it's actually NP hard. And maybe I will briefly talk about why this is so maybe at the moment. So what it means, so on the other hand, okay, it's nice that one could answer this question, or one could say it's probably not polynomial time. So in a sense, it also says that it's hopeless to look for some very clever algorithm, because we believe p is not equal to np. Well, now this thing is hard, so we will likely not find a very simple mathematical characterization of those Kronecker coefficients that are zero or non-zero, because this is of course not a precise statement, but you would think that if you really found a simple and clear-cut one, then you could try into an algorithm. This does not exclude finding a combinatorial interpretation. This is not excluded. Okay. I should also say that, again, it's crucial in these problems that the height of the Young diagrams is arbitrary. If you fix the height, all these problems become easy. You can do it in polynomial time. You can even compute the multiplicity. Everything only grows polynomially. It's not a problem. Okay, so this is somehow a little result. Maybe this is for the experts. Maybe I'll just maybe I'll skip this and then maybe we can zoom into this afterwards. Let me maybe mention an interesting corollary of this proof. So somehow, okay, the way our proof works is basically we show that there's a classical hard problem, and we show that the special Kronecker coefficients solve this classically hard problem. And it's actually the problem. Well, it's actually this problem. So you have a set of points. Say there's some three-dimensional Young diagram kind of object, but it's actually just a collection of points. It's just some point set in the positive octant of Z3. And now for each point set you can form slices. You can sum over all slices. Say in the x-axis you sum over all x slices. You get some numbers. There's 5 boxes in the first one, 3 here, 3 here, 1 there. You can do this for all 3 axes, so you get something like a marginal distribution. So you get 3 collection of numbers. Now you can ask, does there exist a point set which is compatible with these margins? You can go the other way around, right? So you give me a list of numbers, 3, 2, 1. 3, 3, 0, and maybe the third one. You can ask, does there exist a point set such that the slice sums are precisely those? And this is a problem that was known to be NP-hard. And what we basically show is that in special cases, the number of these point sets agrees with the Kronecker coefficient. Okay, and again, you may ask me maybe afterwards, what are these partitions? But the point is that we take a problem, we reduce it to the Kronecker. The Kronecker is at least the sum. And in fact, we have like a whole sequence of these reductions. So it's like, so this is this 3D consistency problem, the problem of the coin sets. And actually there's like 10 more such reductions. So at the end, there was like one, so the 3 coloring problem, for example, is one of these well-known NP-complete problems. We start from one that is called 3-dimensional matching, whatever it is, something about edges or hypergraphs. And then there's this whole chain of reductions, and at the end you have the Kronecker coefficient. And the point is this reduction chain, it's injected. And so what it means is you can take the problem instance here, and you get lambda mu nus, which are an instance for the Kronecker coefficient. And reduction means that whatever this computation problem is, the answer to this problem is yes, if and only if the Kronecker coefficient is positive after the reduction. So basically we have some hard problem instance x. Out of x we compute lambda of x, mu of x, mu of x. This is and if the answer to this problem is yes, then this Kronecker coefficient is g is larger than 0, if and only. So and now the cool thing is that somehow this original problem probably has many no instances, so many cases where it's no. Okay. So this also means there's many Kronecker coefficients that are also 0. So far, okay, of course there's many Kronecker coefficients that are 0. But we can also show that these Kronecker coefficients that we get in this way, they're actually always in this cone. So what this somehow says is that actually there's many, and they're on the boundary of the cone. It turns out, and so what this actually shows is that there's many such holes, right? Because somehow it shows that there's many no answers into this problem. It gives us many lambda mu nus, for which the Kronecker coefficient is 0. But we also prove that lambda mu nu are in this cone, so we know that there's some rescaling effect after which it becomes 1, 0.
And it's for any number of rows?
No, some of the it's more like we take the number of rows are pretty gigantic. It's kind of like it depends on what you start. So you start with something here, And then depending on what this problem is that I haven't described, you get some Young diagrams. And you can bound them, but generically they have like, millions of boxes and hundreds of rows. And actually we don't know how to check that our theorem is correct on the computer. There's no way, because we don't know how to compute these Kronecker coefficients, right? We can only do this for like maybe 10 rows and not many boxes, or 3 rows and many boxes. But in this regime, it's very strange, right? So you can use this, you can kind of use this strange reduction the same way I talked about graphs before in liquid riches. You can use such a strange reduction to produce such examples, right? And maybe, okay, I'm not sure if this has, one can prove a deep theorem based on this, but at least it gives you an existence, it's like an existence proof using this complexity ideas. Maybe one last thing I want to say is that one can also more generally talk about this asymptotic problem. One can basically ask, given as input lambda mu, does there exist a stretching factor such that the coefficient becomes positive? In other words, is the corresponding ray contained in the cone, yes or no? Yes or no. So this is the problem I talked about before, that we actually have lists of inequalities. But we don't know have an efficient algorithm. So for example, this week we were talking about a very similar problem. We were trying to cut down the number of candidates for like faces of this cone, because it's somehow very combinatorically complicated object. So nevertheless, one can prove some results about this. And for example, one can easily show that this problem is in NP. So what does it mean to be in NP? It means I have to be easily able to convince you that a point is in the cone. Okay. And I can use this using this geometric description of the cone, which is now a complete mess. But I had this point in projective space before. Some projective space, CN cube. And I said, from this point I can compute 3 matrices, row A, row B, and row C. And then I compute the eigenvalues, and they will give me always a point in the cone. And so I can just give you this vector as a certificate. You can compute the matrices, you compute the eigenvalues, everything is efficient, and you get the right point. So I can easily convince you that a point is in the cone if by some magic oracle I find this point. So like everything is compact here. It's like n cube variables. Everything here is like in polynomial time. So it's in NP. Of course, being in NP is not a very strong result. We can also show that this problem is in what I call co-NP default. So there's a way of convincing you that a point is not in the cone. And because it's a cone, basically what I have to do is I have to give you a hyperplane that separates, such that the cone is on one side of the hyperplane and the point is on the other side. So what you have to do is you have to be able to, if I give you a hyperplane, you have to be able to efficiently check that it's a correct hyperplane for the cone. And for this, we can use some of these concrete inequalities in the work with Michel. Basically, we have to only compute some determinants, and I can even tell you at which point I have to compute them. So somehow, that again, I can convince you compactly, efficiently, that the point is outside. So somehow we have the situation. I drew this diagram before with NP and co-NP. So I said, okay, this is NP, this is co-NP, this is P. So the Kronecker coefficient itself is somewhere here. So asking if G is larger than 0 or not is somewhere outside here. It's actually NP hard. And now our asymptotic problem is actually somewhere in here. So this is the cone problem. And so, of course, so it's very suggestive somehow that there might actually be a polynomial algorithm. So in the same way that people conjecture that P is not equals to NP, this is some of the conjecture everyone believes, and then a conjecture that most people believe is that there's no NP hard problem which is in NP and in co-NP. So the NP hard problems, like the hardest ones, the complete ones, they are outside here. And the reason is that if you had an NP complete problem inside here, then it would follow that NP equals co-NP. So, but people believe it's not the same. So people believe basically that it's an asymmetric definition. So there's problems where I can easily convince you the answer is yes, but not the answer is no. So for example, think about the graph problem, right? I can easily convince you that the graph has a 3 coloring. I just gave you the coloring. But how do I easily convince you that there's no 3 coloring? Right? I don't know what is the compact certificate. And so there's a belief that actually these things are different. It's maybe, it doesn't imply this one. but it's somehow, somehow many things collapse in computer science if this was false, just like here. And so somehow this is really.
also believe that the intersection is not P. P is not contained.
I think it's not clear. I think it's not clear.
Yeah, then is P.
It's not clear. We cannot prove that it's not true because P could be equals to NP and then they would all be the same. I think maybe there's a weak belief that they should be different, but I wouldn't say there's strong evidence for it. So it could well be that all this is P. I don't think we have.
Actually, if that was true, would prove that
Then we would be
NP
happy.
is
Yes,
different.
yes.
It would prove the conjecture, actually. No?
I guess that's right. Yeah. At least. Yes, at least. Yes. That's right. Yeah. Yes. Yeah, right. Then you could relate that. Yes. Okay. So you could say these are all words. I told you about what people believe, so it doesn't have maybe much mathematical content. Nevertheless, there's some empirical evidence that actually these things are different because people tried for 50 years to find efficient algorithms for some of these NP-complete problems. And also there's some more history of problems in NP and co-NP, like that people actually find P algorithms. For example, well, I guess this latest one, Vergata of Baba is such an example, but there's a couple of others, for example. So I'm kind of, I try to work on this a little bit for this particular problem because of this quantum physics interpretation. So I'm very interested in finding a polynomial time algorithm of checking on this problem. You could also interpret this in a way, modulo these plausible conjectures is really saying the asymptotic problem is an easier problem than deciding if the coefficient is 0 or non-zero. And the only difference, of course, is this failure of saturation, right? So somehow there's really something that makes the Kronecker coefficient hard, this failure of saturation. Maybe I wonder if the language of complexity is more allows one to make more fine-grained predictions. So this I talked about. So maybe with this I should close. So what I wanted to convince you is kind of two things. One is that there's these old coefficients that somehow now have even new motivation to tackle, right? And these motivations from the perspective of, say, this quantum marginal problem, but in particular from geometric complexity theory. Say this matrix multiplication question. There's a similar question about permanence and permanence, which also falls into this theoretical framework. And on the other hand, I think it's interesting, and I propose it's interesting, and I think it's very much underexplored to use complexity theory as sort of a precise language of studying the difficulty of mathematical problems. I think it's not just empty language. I think one can actually learn something by doing so. Because it somehow encodes what we anyways do, right? If there's a problem that we can't solve, we try to think about why is it difficult. And this is just sort of saying, let's actually prove a theorem about it. Okay?
You cannot solve some problem.
Exactly. Then at least show that it's a hard problem, right? If you can solve it, maybe at least show it's difficult. That's like a justification, right? It's a better excuse than I tried for some reason. Anyway, so with this, I'll close. Thank you.